We'll share the screen. All right, everybody can see the screen.
Yes.
Okay, so let's pick up where we left off last class. We were talking about hard drives. Well, really, the starting point of this conversation was talking about the things we should look at when we're comparing computers, and we're going to start segueing this into what do we look like when we're comparing mobile devices. But at the higher level, our mobile devices are effectively computers. So we're not going to make an early differentiation between those two. So last time we talked about things like memory and how much memory you should have, and what's considered good, what's considered bad, things like that. Let's see, what else did we talk about? I talked about processing power and multiple cores. So if I just add, let's just add a slide. What do we care about? So we said amount of RAM, speed of CPU, number of cores on the CPU. All right, let's see, did we talk about anything else before we got to hard drives? I think that,
Battery and
what's this?
battery inputs.
Oh, that's right, battery. So call it battery life slash ports, that kind of stuff. So quality of life stuff, depending on how we're going to use the machine. If you're always going to be tethered to the wall, but you want a computer that you can more easily transport than a desktop computer with a big monitor, well, maybe you get one of the bigger 17-inch laptops or something. But if you are always going to be on the go, moving from room to room, moving to coffee shops and things like that, then you might want to get a much more portable laptop, but maybe something that's still powerful enough to do what you do. If you're going to be traveling a lot, well, then there's that trade-off between maybe you're giving up some of that power for ultra lightweight and kind of compact size, so you can use it on the tray table on an airplane and that kind of stuff. Um, so, uh,
GPU.
and then we also talked about the GPU. That's right. For different applications, and GPU kind of translates into battery life as well. So, like I think I mentioned before, if I bring up on my computer here, this computer has an 8-core Core i9 processor, so a pretty powerful processor, lots of RAM. But notice that I actually it doesn't show it here. Let me go to the, so the graphics is an Intel graphics card. But if I go to system report, I'm guessing it'll show me the other card. Yeah, so notice here I have actually two GPUs in this computer. So I have the one that's built into the main board, and this is the one that is probably using most of the time that I'm playing, or most of the time I'm using my computer, uses a lot less electricity. It can show, word processors and stuff like that on the screen, no problem. And we'll use less of my battery power. Now, if I'm sitting in my office or sitting at home and I'm playing a video game, so for instance, this morning I was here around 7 a.m. and after I got your homework assignment and stuff up, I played one game of Hearthstone, an online card game I play. Well, so that's a game that uses some of your graphic, your computing power. So it probably switched over to my Radeon Pro graphics card. And maybe I would have heard the fans kick on a little bit. And if I had been running off of battery life, maybe it would have taken a little bit longer to play, or it would have taken battery life off of my laptop, something like that. Now, interestingly enough, for those of you who are, so historically, I'm going to give a plug for this game because it's actually kind of fascinating. Historically, I was a gamer, so I used to play games like World of Warcraft and things like that. But as I've gotten older, I just don't have I don't find them fun anymore. I also don't have the reflexes to play those games much. And if you kind of think about the older community, a lot of times I see people at like coffee shops and stuff like that, older guys sitting there playing cards. They're playing poker or blackjack or whatever, some kind of card game. So I kind of started thinking, now I can play cards, but I'm not overly interested in cards. So what's the modern day geek version of playing cards? And so this game I play here is called Hearthstone. It's from the same people who do World of Warcraft. And it's free to play. Forget about the video game aspect of it or whatever. What I have actually found is it's very related to computer science in terms of your problem solving. One of the things I constantly talk about in computer science is that we solve all of our problems in terms of the tools that you have. And, so for example, if you are playing, you have your whatever cards are in your hand and you have to do something to beat your opponent, which is another real human being. And you have to solve that problem in terms of the cards you actually have. It's not as generic as just normal playing cards, playing poker or something. Different cards do different things and stuff like that. And I've actually been using it with some of my students I tutor for computer programming, because I think it actually builds those exact same skills. So interestingly enough, if you were going to be a gamer, or you already are a video game player, I would actually, as an educator, recommend this game as a problem-solving skill set situation. It's funny, the lights in here just went off because there's not enough movement. All right, so in any case, there's my plug for this game. It's free to play. It's from Blizzard Entertainment, but don't get addicted to it. I'm more saying that from a problem-solving perspective for a technology student, this is a better way of wasting your time and still getting some brain power going. Come on in. The lights just went out. I'll turn them back on. Finally, somebody shows up. Gully, will you hit the maybe the second from the top button? Thank you. All right. So in any case, there's my plug for a problem-solving thing. So let me get the AV system. Are you guys on laptops, both of you?
Yes.
Do you want to just jump onto the Zoom thing, or do you want me to put it on the?
I can jump in Zoom.
Jump on Zoom? Okay. Doesn't matter to me, but oh, here, I'll put this thing back on. All right. So in any case, there's a plug for a game that will help you with your problem solving in a weirdly computer science kind of way. Okay. So, that was kind of our segue off of GPUs right here. But, kind of the idea is that the more video gamey you're running something on your computer, the more the GPU is going to end up using. Punchline. Okay, so then we ended up last time talking about hard drives. And we're going to, I actually put your first homework assignment up, and your first homework assignment is a paper dealing with hard drives and the technologies under the hood for them. So we're not going to get too deep into that today. That's going to be something you're going to look into for next class. But if we're talking about hard drives in general, what is the rationale for, so you're buying a computer. This is what we were talking about last time. And you're looking at the hard drive. What kind of things do you look for? What things do we care about with the hard drive?
Space and speed.
Okay, so for hard drives, we care about total capacity, and we also care about speed. Now, sometimes these two things are at odds. So one thing, if you've ever seen this when you were like shopping for a laptop or whatever, and it's probably less common today because we're starting to move away from that technology, but you maybe have seen a computer that comes with a 1 terabyte hard drive, or you can upgrade for to a 500 gigabyte solid state drive. So the idea here is this is half the capacity of this one. Yet this is probably, you know, depending on when you maybe would have seen this, this might have been a, you know, a $400 upgrade, something like that. So you would have paid an extra $400 for half the capacity. So as a normal consumer, you may have looked at this and said, well, why am I paying more money for less, right? Okay, so this ultimately comes down to your understanding of the difference between this technology and this technology. So this technology is an older mechanical hard drive. So, and we'll talk about this a little bit here in a second, but you also research that in your, Willie, do you have your laptop with you? Okay, so you can get on Zoom? Okay, otherwise I'll share on the screen, but I was sitting here alone for a while. So yeah, if you guys are gonna keep coming in person, I'm already here. So I was in my office, but I was just sitting in this room alone for a while. Yeah, just like leave it to grad students. You show up 20 minutes late to class. It's garbage. All right, so in any case, this guy here is a mechanical hard drive, i.e. moving parts. Mute. All right, so it's got moving parts. When we're measuring mechanical hard drives, what things do we look at? What makes one HDD better than another? What do we look at for these kind of drives? Take my sweater off. So if you're shopping for hard drives, what makes one HDD better or worse than another?
Maybe the version.
Okay, give me an example.
I mean, I don't know, but just play slightly. I remember that the previous version, which we used like 10 years back, it's like HDD 3.1, something like that. It will be, it's in a bigger size compared to
Okay,
these HDD.
so we might say speed of the drive. So we care about speed and we care about capacity. So one thing you maybe have seen, similar to this note we have down here, is you maybe have seen, this would have been, you know, probably something like 3-4 years ago would probably be the last time this would have been a real thing. You may have had a computer that came with a 500 gigabyte HDD, or you can upgrade to a 300 gigabyte HDD for, let's call it $200, something like that. So both of these are mechanical based technologies, but you're actually getting, you know, almost half of the capacity for more money. What was the differentiating factor between these two drives? B, you're late. So what was the differentiation between these two drives? This guy probably was a 5,400 RPM drive, and this guy was probably a 7,200 RPM drive. Now, even in some laptops, you would have had 4,200 RPM drives, all right, which would be even slower. So the idea is that for a mechanical hard drive, the faster it spins, the faster the drive is, because, and this is kind of, let me jump to another slide here. How important is hard drive performance?
Very important. Like when you are booting a computer, your hard drive performance does matter actually, because the slower the hard drive, all the functionality in the starting point can be slower.
Okay. Oh, you just switched devices. Well, so now you're on your cell phone, probably driving around, not even paying attention to my screen.
No, I'm on my iPad.
Giving you a hard time. All right. So, Gully mentioned that, it maybe makes a difference for your boot time. Now, realistically, do we actually care about that? I think it's one of those things that like gamers care about, like, oh, my machine took, booted up in 4 seconds rather than 12 seconds. If that was the only difference, do we really care? It's kind of like, when you're, I think we mentioned last time with like converting a video or something like that, or rendering, fine, you can get a computer with a GPU in it where it will render an animation in 3 minutes or 2 minutes or whatever it is, or you can use an older computer that'll do it in an hour. Well, who cares if you're going to just render and leave the room and go to lunch or something like that? It doesn't matter whether your computer did it in 4 minutes or did it in an hour. When you come back, it'll be done. That's the kind of the punchline. So I would maybe argue that the boot up time for a computer related to the hard drive performance is more of like a bragging rights thing, where it kind of makes you feel better about the technology or something like that. But when we say how important is hard drive performance in general, I'm going to give you the punchline here, and I'm going to say very, very, very important. All right. The idea here, in fact, I would say that the first thing, if you have a computer that feels pretty sluggish, feels slow, the first thing you should upgrade after you've gone through the process of just making sure you have enough memory. We talked about last time that kind of maybe your minimum amount of RAM you want to have in a computer today is like 8 gigabytes. I would say from a technologist perspective, the minimum you should have is 16. That would be my opinion. I wouldn't buy a computer with less than 16 gigs of RAM in it today as a technology person. Now, for me, I wouldn't buy a computer like truly for the way I use my computer. I wouldn't buy a machine with less than 32 just because I run a lot of virtual machines. But if I was not teaching, I didn't have to run this thing on a screen and stuff like that, that would probably be overkill. But I wouldn't do less than 16, especially now since so many things are just integrated. But once you have your minimum amount of RAM that you need, and RAM's not expensive anymore, we'll talk about that a little bit in a minute. But once you have the minimum amount, the first thing to upgrade is your hard drive. If you have an old mechanical hard drive in your machine and you swap that out and you put in a solid state drive, even if it's a cheap solid state drive, that drive is orders of magnitude faster than that mechanical drive. And you'll see that when you go and do the research for your paper due on Monday, the difference in speed, it's like the difference between me being on foot versus like a Ferrari. And the reality is that sounds like it's far-fetched. It's not as far-fetched as you might think when you're comparing those technologies. Solid state drives are way faster, not like a 20% increase. Okay, so you will immediately feel your machine being a lot speedier. Because when are you hitting the hard drive on your computer? When is your hard drive being used? Off the top of our head, we might say it's only being used when we're like storing something, right? You're downloading a file, you're putting a MP3 on there or something like that. But when's the hard drive being used in other circumstances? Almost every task, right? We talked last time about the amount of memory, and we talked about virtual memory. So even if you have plenty of RAM, when you launch an application, only a portion of that application gets loaded into your system memory. The rest of it lives in virtual memory on the hard drive so that you don't take up all of your available RAM to hold one application, something like that. So that means that whenever something isn't available that needs to be moved into system memory, it needs to hit the hard drive to copy that into system memory. And the faster the hard drive can communicate with the system memory, the better we are, the faster we are, the faster the machine will feel, things like that. Now, one thing I like to think about computers, how to think about a computer.
I mean, in SSD was introduced for faster performance of OS services, right?
Well, it'd be faster performance for anything, any application that's running, including, yeah, your operating system, system calls and stuff. Everything will be faster because the access time of that hard drive is quicker.
But
One
I
way
don't understand the
Say it again.
point in choosing only 500 GB for SSD and 1 TB for
Okay,
HDD.
so yeah, so you're asking about this guy right here. Why would you choose instead of a 1 terabyte hard drive, you could upgrade to a 500 gigabyte SSD? This guy right here is,
Yes, I mean,
I'm gonna make
we
up a
can
number.
choose 1 TB SSD also, but we choose 500 SSD and 1 TB HDD.
Well, yeah, so
together.
if you're debating between 500 gigabyte SSD and 1 terabyte SSD, then assuming they're the same SSD technology, a couple of, there's some, not all SSDs are created equal, but in general, they're all way, way, way faster than mechanical hard drives. Okay, so let's just assume it's the same technology and you are comparing a 500 to a 1 terabyte, 500 gigabyte to 1 terabyte, then your deciding factor is how much stuff do you store in your computer, right? Go ahead.
So, like for example, whenever, like you said, we have a designated space in memory for every program or for any application. So same goes for SSD and same goes for like the traditional one, right?
Yep.
So both of them have some physical differences in terms of memory. What exactly the difference is for solid state and the HDD?
Like how they work?
Yes,
That-
exactly. What's the allocation process?
Okay, so SSDs use a technology called flash. And we'll talk more about that on Monday because that's what you're going to be researching for your paper. But you're right. Under the hood, they are using the technology. It's not just the hardware. It's also how that hardware is used that makes it faster. And the starting point would be moving parts versus no moving parts. Flash-based technology doesn't have moving parts, which if we connect that back to the mobile computing side of kind of this course, why might that be nice for a cell phone or for a laptop? We drop these things, right? Okay. Hopefully you don't drop your laptop very often. How many of you have ever dropped a laptop? I got some battle wounds on this this guy. It just happened like a month ago. I dropped it on my driveway. That's an expensive repair when you drop a $6,000 MacBook Pro on the ground and nothing broke on the inside because the thing's built like a tank, right? But I had all this expensive metal on the outside kind of chipped off and scratched up and stuff like that. I don't know if you guys can see it from back there, like I have here and yeah, and then up here at the top. And it was a lot more jagged. I was cutting my, also right around here where I put my wrists, I was cutting my arms on it. So I took a nail file and smoothed it out. Not exactly the desired repair, but it's cosmetic. But generally speaking, if we kind of move away from that side of things, a hard drive with no moving parts is going to have a much better chance of surviving a drop, right? In fact, what did we do before we had solid state drives? If you had a laptop that had a hard drive in it, if your machine was running and you dropped it, you probably broke your hard drive. That's really weird that just won't stay on even if we hit the button. That seems to be like problematic because we do have people in the lights keep going off in here. We have the right button pushed. It's got to be like, they must have like the energy saver thing turned on for, All right, Galib, every 45 seconds, you have to wave your arms.
All
Set an alarm. All right, so what would happen, so you were almost guaranteed to lose all your data or corrupt your data if your machine was spinning. So what started happening is they put into the laptops kind of like accelerometers like they have in the mobile devices to lock the hard drive if it wasn't falling. To attempt to like get brace yourself for impact, that type of thing. All right, but to your question, if you are looking at solid state and you're comparing between 500 gigabytes and 1 terabyte, this is just a capacity question. If you download a lot of music and stuff like that, and you keep that on your computer, well, then get the 1 terabyte so you have more storage, right? And we should all know the conversion stuff here. That's important for. Did I have a slide for that last time? Oh, well, we definitely should. All those bits and bytes, because we're going to be working with this a lot this semester. So we'll do this as a team because all of you should already know this. What is a bit? When we talk about computing, what is a single bit? It's a 0 or a 1, right? What's a byte?
8 bits.
8 bits. All right. What's a kilobyte with a big B?
100 bytes.
It's 1,024 bytes. What's a megabyte?
1024 KB.
All right. Gigabyte is 1,024 megabytes. A terabyte is 1,024 gigabytes. Now, why is it 1,024 and not 1,000? Which is actually a little misleading when you think about, where's my slide? I really need to make the color coding like this. When I'm just on a slide here, it's just
It goes in the power of 2 power n.
Yeah, it's a power of 2. Okay, so 1,024 is a power of 2. 1,000 is not. All right, so because we have bits and bytes, and one of the things we're going to get into in here is everything in computers is effectively a power of 2. And the reason for that is because of binary and the number of bits and all sorts of things like that. So if we're dealing on the bytes column, we have a scalar by 1,024 starting with 8. On the bits column, we have a kilobit, which is a lowercase b. So this is 1,024 bits. We have a megabit, 1,024 kilobits. We have a gigabit, which is 1,024 megabits. And we have nobody really says terabit yet, but it's a real thing. So we'll say 1,024 gigabits. Now, the connection I would make this from a technology perspective is for those of you who have, well, all of you have internet at your house, right? One way or another. What's the speed of our internet? 100 what?
100 MB.
Wait,
Mbps.
big B, little b. Big B, nope.
50 Mbps.
It's a little b, little b. See, that's where, so again, I keep going back to this idea that, you should be able to go into Best Buy and not get taken advantage of. And if you think about all the commercials, what do the commercials say? Well, it's 200 meg internet. They don't say the B part, okay? So usually if you buy like from a Spectrum right now, if you have cable modems, for example, I think their low end now in the Milwaukee area is 200 megabits per second. So if you get 200 megabits per second internet, that is megabits, not megabytes. So that means your maximum download speed is 25 megabytes per second. That's your maximum theoretical download speed. Now, do you always get 25 megabytes per second? Nope. Why?
No.
What keeps you from getting 25 megabytes per second?
I think the network is shared by many people.
Okay, well, what if you're the only one? You're the only one in your house, you're the only one in your neighborhood. Because cable modem technology, we're not going to get into that in here, that's more of a networking thing, but cable modem technology does share the bandwidth within a kind of a pod, within a neighborhood, let's say, to keep it simple. But let's say you're the only one home and you're the only one in your neighborhood that's on. Okay, so you get the full 200 megabits per second is available for you. Why aren't you getting 200 megabits per second? Okay, give me an
Maybe
example.
internet traffic.
For example, if you are connected to a LAN and you are the only one, for instance, those signals are converting to 0-1 binary bytes or bits.
Okay, so maybe the conversion, so if you're connected to a wire, maybe it's faster than wireless, something like that. Okay, you could have some latency related to wireless. Okay, but so realistically though, if you look at your wireless router, most of them are capable of, some of them are, there's a gigabit technology now or something like that, but almost all of them are going to be able to handle 200 megabits per second faster than that. All right, so, but again, if you're, if you are one of 1,000 people all connected to a single Wi-Fi hotspot, exaggerating, but yeah, you certainly would have performance degradation. But again, you're the only one home. So why aren't you getting your 25 megabytes per second?
Well, I'd say 90% of the time I'll get it. 10% of the time it depends because I think that's a big variable.
How are you measuring it? You say 90% of the time you'll get it, but how do you know you're getting it?
How do I know I'm getting the service home?
Well, yeah, how do you know you're getting your 25 megabytes per second? How do you test that?
Number of packets sent and received.
Oh, so that's what you do? You sit at your computer and you open up a packet sniffer and you look at the number of packages sent and received?
No. We call it ping for the internet test speed.
Download and upload speed.
On a daily basis, I couldn't test for, yeah.
You do a speed test, right? You do a speed test. So we come over here to, let me- this thing is always in the way, like always. It should hide by default. So if I come over here and I do speed test on Google, and I can, there's other ones out there, but I'll just run a speed test. So I'm on the university's Wi-Fi right now. I'm on Res Hall. Okay, so I got 61 megabits per second down, 42 megabits per second up. All right, not horrible. Part of that is probably signal strength, Wi-Fi, things like that. If I was plugged into a wired network, I probably would get faster right now, but I still would not get the maximum speed. I wouldn't get the amount that Concordia pays for. Okay, my maximum download speed is whoever I am downloading from's upload speed. Does that make sense? So if I go back here, if I have a 200 megabit per second connection and the person I'm downloading a file from has a 20 megabit per second connection, the maximum I'm going to download from them is 20 megabits per second. Even though I'm capable of pulling it at 200, they're only capable of giving it at 20. Does that make sense? Okay, think of it like if we'll put it in a real life example. Have you ever gotten like in your shower at home, you get a new shower head and all of a sudden the water pressure is way better? Okay, it's because even though the water coming to your house was enough, the shower head could only put out so much based on, it wasn't able to fully deliver the water pressure that your household water was giving it. And by getting a different shower head, you were able to, it kind of buffers it and, gives you more pressure, that kind of stuff. All right, so you have that kind of comparison where you're dealing with bandwidth, where you are at the mercy of whoever you were downloading from. And I would say very rarely, unless you're downloading something from one of the big boys, like Google typically does have quite a bit of bandwidth. So, you can probably get pretty close to it if you're downloading a patch from like Microsoft or something like that. You won't always maximize your connection, but you can probably expect faster speeds, right? But probably still not maxing out your connection. They're probably not maxing out your connection. So why buy more internet than you can use? So even the baseline from Spectrum's a budget pleaser internet. You're not even getting all that. So why buy their turbo or their gigabit internet? So gigabit internet is 1,024 megabit, right? Divided by 8, that's 128 megabytes per second maximum download speed. Why would you ever buy gigabit internet if you can't even get your maximum speed for your 200 megabits per second internet? Is it bragging rights?
I think maybe because that will be giving a little less speed than the maximum one.
Probably not. If the person you're downloading from can only give it to you at 20 megabits per second, it won't matter whether you have a 200 megabit per second connection or 1,024 megabit per second connection. The fastest you're going to download it is 20 megabits per second. So why pay for that extra bandwidth?
Well, I think it depends on the application here. If I'm like a gigabit speed, if I'm a professional person, multitasking with multiple things, I need that speed. If I'm, for example, a streamer, and working other things while I'm streaming, I need that speed.
Okay, so you mentioned a couple different things there that both are important. So one of them you said is if you are using it for lots of applications. So while you might only be able to download from a single source at a maximum speed, if you are simultaneously downloading from 4 or 5 different sources, that's going to start adding up. So if you're streaming Netflix at the same time as you're playing a game, at the same time as you're downloading music, at the same time as 3 other people in your household are doing the same things, all of a sudden that total bandwidth pipe starts making a difference, right? If you live in an apartment with 4 different people and you guys are all streaming stuff at the same time, you might start getting pretty close to maximizing your internet connection if you're streaming 4K, right? Okay, so that's one thing. So it's kind of more from a number of devices or a shared resource perspective. Now, let's say on the flip side, you are streaming video, doing like a live video. So, I mean, right now I'm not live streaming on YouTube because I actually record on Zoom and then upload to YouTube. But let's say I was live streaming on YouTube. Most internet connections, like when you download a 200 megabit per second, when you buy a 200 megabit per second internet connection from like Spectrum, what you're actually getting is 200 megabits down and something probably more like 10 or 15 megabits up. So your upload speed will very likely be substantially slower than your download speed. Why do they do that? Why do they sell you a connection that is a lot faster downloading than it is uploading for consumer internet? Business internet typically is, so that's called an asynchronous connection, where one of the directions is faster or slower than the other. Typically, it's the download is faster, the upload is slower. Where business internet is usually synchronous, where it's the same speed upload and download. Why is that? Why is consumer internet faster download but slower upload?
Because consumer they only needing the approach of downloading more things rather than uploading.
Okay, what are some examples of uploading? So a consumer definitely downloads more, right? Almost everything we use our internet for is to consume data. We're consuming Netflix, we're consuming email, whatever it is. Those are things that we're using our download for. When do we use our upload?
like
upload a 4K
pictures.
video, pictures and videos to the OneDrive, to the Google Drive.
Okay. So if we have like a folder with OneDrive or Dropbox or something like that, and we put something in the folder and it automatically uploads it to the cloud to store it, that's using our upload. Attachments for emails, that's using our upload.
Yeah, well, basically, uploading is relative to downloading is very simple task, but I'd say also browsing is uploading.
Very tiny.
Very tiny.
Yeah, you're sending a request.
Yeah.
Get me this page, but Galib, 45 seconds. Every 45 seconds, you got to wave those arms.
I think I thought the was.
You think that's it? You're gonna hit the top one to just keep it on? Because I told him to hit the second to the top one, but whatever, we'll figure it out. Yeah, it's true. You are using uploading often, but it doesn't require a lot of bandwidth. So that is one thing. The other thing that the Spectrum doesn't want consumers to do is they don't want you to, oh, you're looking for the plugin? One thing that the consumer, that Spectrum doesn't want consumers doing is they don't want you running servers out of your house. Okay, so they have two ways of combating that. One is they give you a slower upload speed. So even if you were running a server, you're not going to be, you're now the person who can only give the data to somebody at 10 megabits per second, regardless of how fast their download is, right? So even if you are running a server, you're not the fastest server around, okay? Not even close. Secondarily, well, I lost my train of thought there. So they want you to not run servers out of your house. So that's what that upload is. How do we, as consumers then, how do we get around that? Okay. Tell me about BitTorrent. I don't want to get too far into the networking side of things, but technology like BitTorrent has become very popular. I mean, sure, it's used for a lot of, downloading movies and things like that we probably shouldn't be doing, but it's also used for a lot of software patches and things like that now. So how does BitTorrent, since usually when we're doing software patches, we're consuming that over our consumer internet, how does BitTorrent get around this upload speed issue?
Maybe like they have some like what do you call it? An AI engine that is determining on runtime that which pair is sending maximum load speed, so that if I'm using the same patch, so I can just catch up with that pair and then it can pair me up.
Okay. So we're kind of back to this slide here where we talked about bits, hence the name BitTorrent. So whenever you're downloading a file on a computer, it's a collection of bits, right? So files on a computer are a collection of bits. Now, if I had a bucket over in the other side of the room that had a bunch of apples in it, we think of those apples as like bits, all right? And I want to ultimately get all the apples to the front of the room here. Could each of you go over and grab a handful of apples and bring them back here independently? So you're using your internet connection, you're using your internet connection, you're using your internet connection, and you're grabbing the apples, bringing them up to the front one at a time, two at a time, whatever it is, right? Now, what if ultimately the job was, what if you had some of the apples, you had some of the apples, you had some of the apples, and ultimately the goal is to get them up here? Can I get some of the apples from you and some of the apples from you and some of the apples from you? And even though you can only give me apples so quickly, I'm able to get apples more quickly than you can give me apples. But between the three of you, you can give me apples 3 times faster. And maybe that's getting closer to my speed of consuming apples, right? So if I have a 200 megabit per second internet connection and I can't download from Galib at 200 megabits per second, but instead I can get stuff from him at 20 megabits per second, and then I find 10 other people who could also each give it to me at 20 megabits per second, Now I can potentially maximize my internet connection by downloading from 10 different people, each who can give me it at 20 megabits per second. And because the file I'm downloading is ultimately a collection of bits, if all of you have the entire file right now, let's say, you don't necessarily have to for BitTorrent to work, but let's say each of you has the entire file. There's 3 people in here. I can download a third of the bits from you, another third of the bits from you, and another third of the bits from you. And now I have 100% of the bits that I grabbed from 3 different sources, getting closer to maximizing my internet connection. That makes sense? So we want to think about the data that flows on the internet, that flows on our computers as bits. Okay, and even though most of our software applications might be multiple gigabytes in size, you know, ultimately at the end of the day, that is just a giant collection of zeros and ones. And it doesn't matter where I get my zeros and ones from, as long as I get them all and they're in the right order. Does that make sense? Okay, and that kind of becomes more of a networking thing, the way TCP/IP works and stuff like that. So that's not a subject for this class, but the punchline is for us, we're always operating on bits, zeros and ones. All right, so we should definitely understand this conversion table. Okay, we need to know when something has a little b, we're talking about bits. When something has a big B, we're talking about bytes, and we should know the scalars between them. So if on a test or something like that, I gave you some, you know, if I asked you how many gigabytes per second can you download, can you theoretically download at on a 200 megabit per second internet connection? Well, you would go from 200 divided by 8 gets you to megabytes. Divided by 1024 gets you to gigabytes. So a 200 megabit per second internet connection has a theoretical maximum speed of 0.024 gigabytes per second. Make sense? Okay, so punchline for us, all right? We should understand what these different things ultimately end up meaning. Now, click. Oh, just arrows don't work anymore? That's just a thing. Moving parts for the hard drive there's things called platters. So inside they spin. And there's this little needle that's kind of hooked into all the different platters, and it's called the read-write head, that's used to find a place on it, almost like a record player. It's a simplification, but that's roughly what it is. Okay, let's see. From here. Why is that? All right, so how do I like to think about a computer when we talk about the architecture or the organization of a computer? I like to think of it like kind of like roads, like an interstate system. All right, so just none of it. Yeah, it just doesn't work anymore, I guess. Let's close that. Let's reopen that.
Oh, by the way, happy birthday.
Thank you. It's my 21st birthday today.
Oh, it's your birthday. Happy birthday.
21st. You believe that? I made it. Is it what, 21? My 100 times 21?
100 minus 21.
Oh, 100 minus 21. No, it's younger than that. But it's correct. It's not my first 21st birthday. I've hit that number a couple of times. All right. So how do you think about a computer? So I like to think about it like a road/highway system. And what I mean by that is some roads are faster than other roads. Now, when we're traveling long distances, our preference would be to be on faster roads, but that's not always possible, right? So if we're going from here to like Wauwatosa, for example, we get to travel on several different roads. Now, the distance between here and Wauwatosa is is it possible for us to travel a longer distance in a shorter amount of time than it is to travel a shorter distance? Like if the roads were slower. So I can probably go from Mequon to Wauwatosa in, let's call it, close to a straight line, taking, neighborhood paths and side roads and stuff like that. Or I can take 43, the interstate, down to Milwaukee, and then take 94 across to Tosa. And I'm probably ultimately going to travel a further distance, but probably in a substantially shorter time period because of the speed of those roads allow me to travel. Does that make sense? Okay, so inside of our computer, we have multiple different roads. Okay, so we have these components of our computer that we're talking about here, and they're all connected to each other, typically through a motherboard, right? They're all plugged in through this motherboard, but that motherboard is effectively, think of it like the city, right? And in this city, we have roads that connect all these different things to each other, and some of those roads are faster than other roads. So one of the things is called a front side bus and all this stuff. So, important, but not that important for this conversation. But bottom line is not all of those roads are as fast as other roads. Similarly, we also need to store stuff pretty often inside of a computer, okay? As kind of almost like going through toll booths, okay? We can think of them like toll booths. So if you've gone through Chicago and you don't have one of those, the iPasses, then you have to stop at all the toll booths, and that can take some time, and sometimes they get backed up. Okay, so some toll booths are faster than other toll booths. So depending on where you're ultimately going, if you have that iPass in Chicago, you can go through all the tolls. You still get charged, but you can get to your ultimate destination much more quickly because you're not having to slow down, right? So when we're talking about inside of a computer, these various toll booths, what we're really talking about is kind of like the various memory chips. Okay, so things that we store. Okay, so we were going to say roads allow data to flow between components of the computer. Memory is like a toll booth where not all toll booths are created equally. Typically, we might say with computers that the smaller and closer to the CPU memory is, the faster it likely is, and the more expensive per bit it likely is. All right, so if we think about what does this ultimately mean, cost of memory, our cheapest form of storage in our computer is our hard drive, followed by system memory, followed by cache memory. And you have a couple different kinds of cache, L1, L2, L3 cache, and we'll talk about those at some point. Followed by cache memory, followed by hardware registers. Okay, hardware registers live on the CPU. That's really quick road. It's like stepping out into your front porch, right? Okay. Not a whole lot of distance to travel, and it's fast. All right, it's really fast. So now if we use an example, so again, this goes back to my idea of understanding, if you go to not getting taken advantage of in Best Buy, you know, because as technologists, we should understand these hardware components, right? Okay. So if you're buying memory for your computer, let's say, how much is, if you have 8 gigabytes of memory currently in your machine, and your machine is an upgradable machine, how much is another 8 gigabytes of memory today? How much? $400. $100. Way less than that.
60 maybe.
$60 for 8 gigabytes?
I don't know. I never buy it in US, so
Yeah, let's $32. You looked it up on Amazon? All right. So 8 gigabytes of memory is $32 in 2021. Okay. Now in 1994, I bought an 8 megabyte memory chip. How much do you think 8 megabytes of RAM was in 1994? $100? Okay. At least he's adjusted. He thought it was $100 to $200 for 8 gigabytes today. Okay. Nope. More.
50.
How much? 600?
250.
$250? More.
500?
More.
More? 1,000?
$1,000.
What?
So 8 megabytes of memory in 1994 was $1,000. Megabytes. So 8 gigabytes is how many megabytes? 8096, right? 8 times 1,024. Oh, 8192. So we can rewrite this as 8192 megabytes of RAM was $32. So that means that if I take 32 and I divide it by 81, let's do it, we'll probably do it in pennies maybe. Well, this will be in dollars, that's fine. So 32 divided by 8192 is $0.004 per megabyte. That's how much it is today. Which means that by today's cost, in 1994, my 8 megabyte chip should have only cost 3 cents. But it cost $1,000. So 1,000 divided by that means memory is 32,000 times cheaper today than it was in 1994. And the punchline is in 1994, the cost of memory had already come down some. It used to be even more expensive than that. Memory used to be very, very, very expensive. Now, just load it up. You know, you buy a laptop, especially if you're buying something from Apple, so you got a 13-inch MacBook Pro. So you probably maxed whatever the memory was on it because that's what made sense, right? Even though you had to pay Apple a premium. So Apple's 8 gigabytes of memory probably cost a little bit more than $32 for the upgrade, but you're at their mercy because it's not upgradable, right? It's on the chip. It's inside there, okay? So the punchline is that memory used to be very expensive. It's much, much, much less expensive today. So by today's standards, we care much more about the speed at which computing occurs as opposed to the cost associated with memory. Now, we started off this discussion today talking about the importance of hard drive speed. I would say after making sure you have the minimum amount of memory in your computer, your hard drive speed is the most important feature of your computer that makes it feel fast. Okay, so if you have an older laptop that you feel is a little bit sluggish and you don't want to buy a new laptop for probably as little as $70 or $80, you can get a decent size solid state drive for a laptop. There'd be a 2.5-inch drive, and put it into that laptop and probably make it feel 20 times faster just by making that one change in your laptop. All right. So hard drives are a big deal. So your homework assignment for Monday is to write a 3-page paper. It's already up on Blackboard. Is to write a 3-page paper discussing the different hard drive technologies that are out there. So there's some flash-based technologies that are already available. So you're going to compare and contrast those, and then also compare them to the speed of our historical mechanical hard drives. So you really get a feel for the difference in speed between them, their capabilities. All right, make some sense? All right, so back to here. So we care about amount of RAM, the speed of our processor, number of cores, our battery life, our GPU, our hard drive. What else do we care about with our computers when we're shopping for a new computer? Yeah,
Maybe
right. Display size. And we'll say /resolution. That's a little bit more set today than it used to be. It used to be much more, because I mean, now you basically get a new screen, and it's probably a 4K screen or something, in that neighborhood, where historically you would have bought monitors that maybe had different resolutions, and or you was capable of different resolutions, and the higher resolution you run something at, the smaller everything is, but the more stuff that fits on the screen. Something like that. All right, so, but generally speaking today, what we really care about is the display size, right? All right, so for a laptop, is a bigger screen always better than a smaller screen?
A bigger screen is better.
Is it? Or does it depend?
It depends.
Depends what you're going to use it for, right? So I have a 16-inch screen on this laptop. He has a 13-inch screen on his MacBook Pro. So there's two possibilities. The reason that he got the smaller screen could be because by staying in the 13-inch class of computer, you save some money, but it also could be for portability. I mean, fine, this machine is pretty portable, but not as portable as his is, not as light as his is. It's not that this machine is overly heavy, but his machine would be even lighter. But now, why did you get a 13-inch MacBook Pro instead of a 13-inch MacBook Air? Why did you choose to get the Pro rather than the Air?
Because previously I don't have good experience using MacBook Air, maybe performance issues.
Okay.
And I found, I read online about the differences. So MacBook Pro is more compatible in terms of programming and stuff like that.
Okay. Yeah, so really, I mean, this question I'm asking you is exactly what we're talking about in these slides, right? What made him ultimately decide on that computer? He could have gone the direction of ultra portable with a 13-inch MacBook Air. They actually used to have an 11-inch MacBook Air, which I had one of those. It was one of my favorite machines. It was a really convenient computer. But you traded off some stuff, right? So he could have gotten a maxed out MacBook Air, 13-inch MacBook Air, for probably a similar price, if not a little bit less money than he spent on this computer. But let's just call it within spitting distance, right? And it would have had the same screen size as the computer he got, and it would have definitely been lighter. But was it that much lighter? Well, a human being might say, well, this is already pretty light, but it was probably, I'm guessing it was probably less than half the weight or something like that, or close to it. You know, it is lighter. It's definitely lighter. It's definitely more portable. It's definitely thinner. So if you travel a lot, maybe that MacBook Air is the better choice. But he said, hey, you know, I'm a student studying computer science, and you know, while I maybe don't want to spend the money to get the even larger screen of the MacBook Pro, 16-inch, I think it's worthwhile investing in a little bit beefier 13-inch MacBook Pro rather than the 13-inch MacBook Air that maybe has a little bit less system resources, smaller hard drive, less battery life. Well, not necessarily less battery life, but less performance at the same battery life, right? You know, you probably get 10 hours of battery life-ish on both machines under, let's call it just normal use. The difference is that, you know, the MacBook Airs have kind of a low cost or low power CPU in them, whereas the MacBook Pros have a more powerful processor in them. So you're making a trade-off there. All right. So it's not a matter of which one's better or worse, it's which one was the right fit for you. Okay. You know, a bigger screen often can be better, but there's certainly situations where it's not. Just is what it is, right? Okay. So display size and resolution. Anything else?
Thermals,
Say it again.
temperature of the CPU.
Temperature of the
General.
CPU. So when you go into
Yeah.
Best Buy and you're shopping for a computer, you ask them to tell you about the temperatures of the CPU.
No, I generally watch YouTube reviews before
Okay.
buying a laptop.
Well, aren't you kind of at the mercy of, I mean, if you're getting a kind of a pro class machine, you're at the mercy of whatever the temperature of an Intel processor is, Core i9 or Core i7 or the compatible or the comparable AMD processor, something like that. So you might care about the heat of it from an overclocking perspective once you already have the machine and you're thinking about overclocking the CPU and what kind of liquid cooling or something like that you might need. But in general, that's probably not something you care about when you go and buy the ultimate computer, or you're ultimately going to buy the computer. All right, anything else we might think about? There's this kind of cover the big boys. Okay. So when we think about computer architecture, what are we really thinking about? We kind of started talking about this a little bit already. But one thing is we're talking about system design. Okay, and all of our computers today basically follow the same system design where we have CPU or multiple CPUs that are connected to each other through a motherboard, and we have these highways that connect them to each other, and then we have those different toll booths along the way that allows data to flow from the hard drive to the system memory to the cache, ultimately to onto the CPU. All that is kind of helped along by an operating system that's running on top of that hard drive, right? Or on top of that hardware. That decides what's the next thing to get CPU time. And especially that becomes more complicated when you have multiple CPUs because you need to make sure that things don't happen out of order and stuff like that. So it's certainly this marriage between the hardware and the software that brings our ultimate computing experience to the surface. But you know, our system design has been the same for a while with just some new magic tricks for the CPU that kind of pop up, and we'll start talking about that here pretty soon. All right. In fact, actually, let's spend just a couple of minutes talking about that to kind of tee us up for Monday. So I don't think I said this yet, right? Oh. Let's go here. So what is the CPU? You know, when I ask that question initially, I usually get an answer something along the lines of the brain of the computer, you know, something like that. What does that ultimately mean? I like to think of the CPU as a collection of magic tricks. And I maybe even mentioned this last class, I don't remember, but you know, if you if all of you hold your hand up, you got to do it. You got to actually hold your hand up and wiggle your thumb. I thought I was the only one who could do that. Okay, wiggle your index finger. All of you can do that. Can you do them both at the same time? Wow. Okay. Now, are any of you impressed that I can do that? You should be a little impressed. Okay. Nothing about that is impressive in and of itself. But when you think about the number of things that a human being can do, you can wiggle your thumb, you can move your individual fingers. Any individual movement like that is really uninteresting. But you start stringing those movements together and you can accomplish tasks. Pick up a coffee mug, pick up a soda bottle, whatever it is. Okay. So you can think of those little tiny movements that a human being can do as kind of like the magic tricks on a CPU, where each one of those magic tricks aren't that interesting in and of themselves, but you start stringing them together in the right order and things can get accomplished. That makes sense? Okay. You know, the idea here is that if I go back to this slide here, when we talk about that instruction set architecture, this is the names of those magic tricks. Typically, they're on the CPU. They're organized in binary. You know, so if you have a 16-bit or a 32-bit or a 64-bit CPU, typically that does have something to do with the total number of instructions that are possible. Okay, so if we just make the assumption that in modern computer architecture, when you have a 64-bit CPU, that would imply there can be a total of 2 to the 64th, which is a big number, unique instructions. Now, I promise you right now, there are not that many unique instructions in our CPUs. Okay, chances are the subsystem probably uses a smaller piece of memory to actually hold the architecture. So it probably says maybe it's 16 bits, maybe it's 2 to the 16 or something like that. You know, 65,000 instructions, even that would probably be overkill. 256 different instructions, that might be underkill. So I bet you that 2 to the 16th is probably fairly common, but this is really amount of, you know, the memory they onboard on the CPU to make sure it can hold the instruction set. Okay, because if you think about that from a human being perspective, in our head, we remember all the little things we know how to do. We remember we can wiggle our thumb, we can wiggle our index finger, and all the other things. But it's not an infinite number of things that we know that we're aware that we know how to do, right? Okay, so you know, if we just kind of operate off of, you know, this kind of goes back to what I said earlier, even when I was like pitching the card game thing. Okay, we solve all the problems in our life in terms of the tools we have available to us. Okay, if you're playing that card game, you have to solve the current problem in front of you based on what cards you have in your hand. If you are solving a problem as a human being and you don't have any extra tools laying around, you have to solve the problem in terms of the stuff you bring to the table, right? We were getting a TV out of my basement yesterday, an old TV, and 2 guys came over to grab it. I gave it to them. Well, why did they bring 2 guys? Well, because it was an old plasma TV. It's really heavy, and one of the guys thought he could do it, but he couldn't do it. It would be bad. All right, so you know, the idea is that we solve all of our problems in terms of the tools that we bring to the table, and we might say that the more tools that we have, as long as they're related to the kinds of problems we solve, the more tools that we have, the more flexible we are in terms of the problems we can solve, right? So if you're a mechanic and you have a giant garage filled with all sorts of different tools, you can probably solve a larger classification of problems, or at the very least, certain problems you can solve significantly more conveniently than somebody else who maybe just has a hammer and a screwdriver, right? Because they kind of have to just make do with what they have available to them. So when we think about that instruction set architecture for a CPU, what we're really saying is what is the list of tiny magic tricks, tiny little computer programs made out of hardware that processor knows how to do. Ultimately, it's going to be the computer programmer that's going to call upon those magic tricks in a certain order to accomplish real things. All right. So what we'll do next class. Okay, we're going to look at the Hello World program in Linux, which maybe you've seen in one of my other classes before, because one of the things that I like doing, and actually I learned this concept from Dr. Locklear years ago. One of his kind of go-to moves is his idea of the grand ideas of computer science, where all these different fields of computer science are all interrelated. So even if you've had multiple classes with me, you might hear me repeat the same lessons multiple times, but from a little bit different angle. Make sense? So we're going to look at the Hello World Linux program here. We're going to look at it from the perspective of the individual instructions that translate. We'll be looking at an assembly language program, the individual instructions that translate into those magic tricks on the CPU. But we're also going to see the role of the operating system a little bit there, which we don't necessarily care about in this class. But as technologists, as computer scientists, we do care about the role of the operating system, because all these things have to work together to make our world work, make our computer science world work, right? Okay, but the reality is from the focus of this class, when we look at the system calls next time from Linux, those aren't going to be part of what this class is about. But for instance, later today, I'm teaching a systems programming class. We're going to look at that exact same example, and we'll be interested in the assembly language, but the focus of that class is those system calls that Linux is providing and how it's working with the architecture to accomplish even more complex things. Make some sense? All right, questions, comments, concerns, bribes?
Can you upload the slides into Blackboard?
They already are. There's already a link for the slides on Blackboard, right?
Are we supposed to use the virtual machine of Linux?
For what?
I mean, you said you'll introduce to Hello World Linux, right? So
I'm
are we
gonna be
supposed
talking. Don't worry about that right now. The homework,
Okay.
the homework for Monday is a paper. I'm going to be showing you instruction set stuff on Monday by just looking at a Hello World example written for Linux assembly.
Okay.
You're not using that at this point. So focus on what's right in front of you, and that's a paper.
Is the slides under YouTube video?
No, I think it just says course slides over on the left.
Because I don't see any.
Are you lying? Let's see. All right, should be there now. All right, I will see everybody on Monday.